Okay, good afternoon. Today, yeah, one of the lights, thank you. Should be okay, I won't have the board on, but today we're going to work on the next lab. So I got 2 days for Lab D, the Biot-Savart Lab. They're French, so you don't have to say all the letters in their name. These two were responsible for measuring and coming up with the magnetic field strength around current carrying wires, and specifically how that varies with distance. So we're going to use a technique similar to one that some of you used in the previous experiment C by comparing the magnetic field strength from a long straight wire, like the ones that we used previously, to Earth's magnetic field. And for our purposes, I don't really care if we go back and say, here is the strength of Earth's magnetic field, so here's a numeric value for ours. That would be cool. But we can actually get a lot of information even just using the comparison directly to Earth's magnetic field. So, I want to make sure I've got you here. We're going to do, each group is going to have 2 lengths of wire. So what they said is, no wire is infinitely long. So it's interesting to look and see how different lengths of wire affect this. Here's the basic setup though. It says that you'll have 3 lengths of wire to test, but I only gave you room for 2. So I think we'll go with 2. We'll measure the strength of the magnetic field compared to the Earth's. So what we want to do is place our wire straight down. Now, what direction, and if we have current, say, going from your left to right, and we're testing somewhere above it, what direction is a magnetic field going to point from this?
Our left to right.
Right-hand rule, current going this way. Field curves around it like so. So above, it would be pointing this direction. That means that so it's going to deflect things at a right angle, essentially, to the wire and the current going through it. That means for this setup, if I want to compare the strength of that to Earth's magnetic field, I want to have this wire aligned with Earth's magnetic field, so that's pushing, depending on the direction, either left or right. And we can see how far this is going to deflect. So I'm going to have this long wire going left or right. Then I want to measure how distance away from these wires affects the strength of the magnetic field. And I'm not going to change anything else about it. So to get the distance away from it, I'm going to use these handy-dandy blocks to just step it up. So my first setup, and you guys won't be able to quite see this, but I'll be around when you need to. And I'm going to take one of my compasses that has good angle measurement on it and put it down. Now, try and keep everything else electrical or iron away from this while you're doing the setup. Afterwards, we're going to have to do this. But I want to set this up and put my compass right above my wire and make sure that I align both of these perfectly north, at least as far as the compass is concerned. Yes, ma'am. I already apologized because they could not. As soon as I turn on my current then, I should have a magnetic field around this wire that's going to push the magnet off to the side. So if I am drawing this up on the board, magnetic field from Earth is pointing north, so that's the B Earth. And my current is going along this wire. Current going along this wire means magnetic field from the current should be going that way above it, so out of the board. My compass here is initially going to point north, but then because of the magnetic field from this wire, it's actually going to be deflected some amount so that it now points off to the right. Or left, doesn't really matter which direction. And I'm interested in what is this angle, because here, this side is magnetic field from the Earth. This side is magnetic field from the wire, and there is an angle in between them.
It's theta.
Yes, it's theta, the old nemesis. We have opposite and adjacent. That means tangent. So the tangent of our angle theta should be equal to the magnetic field from the wire that we're interested in, divided by the magnetic field of Earth, that we, if we don't know an exact value, at least we would all agree in this room that it's the same. And I want this I want B wire. So if I just rearrange that, we take the magnetic field from the Earth, just call it B, times that tangent of the angle that we measure. And then, after doing that, I want to see how different lengths of this wire affect the strength of this and how it goes away. So with each length of wire, you'll make a measurement, add 2 blocks, put your compass back down, make the measurement, add 2 blocks, put your compass down, keeping everything else the same. And measure how much deflection you get each time. Yeah?
The compasses do measure the angle, right?
Still measure the angle at each new height.
Do the compasses have like degrees on them?
Yep.
Okay.
Yep. The larger compasses have it marked out by the degree at least. Now, as far as lengths go, this wire is, let's see, 60 centimeters. In order to get different lengths of the wire, all we have to do is carefully clip to 2 different points. So this wire would be 25 centimeters if I put the clips here, because the external, or the parts beyond my fingers, aren't carrying current. So the actual part contributing to the magnetic field is only this long. Right? Current would only be flowing between my fingers, not in the part above or below my fingers. So there'd be no magnetic field contributed from those parts.
So do we enter that number into segment length?
Yep, that'll be your segment lengths. So we've got 60 centimeters total, and then your compass would go in between them. And for those of us in class, we've got 16 people, so that's at least 4 groups. So let's say we have a 10 centimeter, 20. Oh, you'll do it.
No, we'll be.
And we need 2 more, so let's do some nice numbers. Let's do a 5 centimeter.
25.
I guess 25 would be good.
How many days is that?
I'm sorry.
Okay, so I'd like each group that gets together, when they're getting materials, pick out 2 of these and check them off, or write one group member's name on it, so that we'll know. Because I want each person to do a couple, and then you'll see on the back side of this, we're actually going to get all of those data together and compare them, because then we can actually write an even more inclusive formula that describes this, taking into account the length and the distance away from the long straight wire. One of these aluminum rods is in back already, the other 3 are up here. I think those are going to be our best bet for this. Okay? Alrighty then.